Good morning children. Today in this video we will learn about rational numbers as well as irrational numbers and how to prove irrational numbers also. First of all, rational numbers. Already we have discussed about rational numbers. Rational numbers are in the form of p by q where q is not equal to 0. Both the p, q are integers. The HCF of p and q is always 1. If p by q form satisfies these all three conditions, then only that p by q form is considered as a rational number. Then rational number can exist in the form of terminating decimals as well as non-terminating recurring decimals. Terminating decimals in the rational numbers can be represented in the form of terminating decimals. Non-terminating recurring decimals. Non-terminating recurring decimals. What are terminating decimals? Terminating decimals is nothing but division should be completed. Suppose if we take 1 by 4, if we divide 1 with 4, we will get 0.25. Means division have completed. Remainder we get as 0. In the same case, 1 by 8. 1 by 8 is nothing but 0.125. Here also division have completed. So 0.125 is decimal notation of the 1 by 8. Suppose if we take 1 by 3. 1 by 3 is nothing but 0.3333 so on. Here division should not be completed. That means we will never get 0 as a remainder. Such that here one of the number continuously repeating, recurring. Therefore, these are considered as non-terminating recurring decimals. Suppose if we take 1 by 11, it's nothing but 0.090909 so on. Here also division is not completing and some number is repeating. What number is repeating? 0909. Such number is repeating. That's why these formations are called as non-terminating recurring decimals and these are called as terminating decimals. So to identify easily, we will use fundamental theorem of arithmetic. How do we use fundamental theorem of arithmetic to find terminating decimals or non-terminating recurring decimals? To identify that, we should take the denominator prime factorization. The prime factorization of the denominator is if in the form of 2 to the power of m into 5 to the power of m, then we will get the terminating decimals. In the prime factorization of the denominator, q is in the form of 2 to the power of m into 5 to the power of m, then whatever the given p by q form is having terminating decimals. If not, then we will get non-terminating recurring decimal. Suppose if it is in the form of p by only 2 to the power of m into 3, otherwise p by 5 to the power of m into 7. Any other way existed means then we will get the non-terminating recurring decimals. Then what are other numbers? What are irrationals? Irrationals are nothing but non-terminating, non-recurring decimals. Suppose if we take some non-terminating, non-recurring decimals like 1.41421356237 so on. Here no number is repeating. In this case, first of all, division is not completed and no particular number is repeated. Therefore, these are called as non-terminating, non-recurring decimals. And one more example, 1.732050808757 so on. Here also this division is not completing and no particular number is repeating. Not only this, one more example, 2.23606797749 so on. This also non-terminating, non-recurring decimal. So how they are existing means they are existing as root 2, root 3, root 5. So root 2, root 3, root 5, these are considered as irrational numbers. Irrational numbers are nothing but q dash. What are irrational numbers? Irrational numbers are non-terminating, non-recurring decimals. Non-terminating, non-recurring decimals are nothing but irrationals. So how do we prove these irrational numbers are irrational? To prove these irrational numbers are irrational, we will apply indirect method of proof. To prove an irrational number is an irrational number, we will use indirect method of proof. How do we use this proof? Let us take one example. Prove that root 2 is an irrational number. Root 2 is an irrational number. Already we discussed, to prove an irrational number is an irrational number, we are using indirect method of proof. In that case of indirect method of proof, whatever the things we are required to be proved as, that one we will assume it as a false statement. Here the correct statement is root 2 is an irrational number. So we would take this one as a false statement. So what sentence we will get if we consider it as a false statement means root 2 is not an irrational number. So by assuming that is not correct statement means assume root 2 is not an irrational. So root 2 is not an irrational means root 2 is a rational number. So root 2 is a rational number means we would adapt to this one as definition. Root 2 becomes in the form of p by q. So already we have known that p by q is a rational number means it should satisfy three conditions. One condition is q never be 0. Other condition is both are integers. Other condition is HCF of p and q is 1. If that both p and q satisfy these three conditions, then only p by q form is a rational number. Okay. Next one, terminate this square root. How do we terminate this square root? By squaring on both sides. On squaring on both sides, we will get root 2 whole square is nothing but p by q whole square. So root 2 whole square is nothing but 2. Under p square by q square. Under cross multiplication, we will get 2q square as a p square value. It is clear 2q square is nothing but even form. Means multiples of 2. Multiples of 2 always divisible by 2. Means p square is divisible by 2. P square is divisible by 2 means definitely p divisible by 2. If p square is divisible by 2, then p is divisible by 2. P is divisible by 2 means it is in the form of 2 into something. On squaring both sides, you will get p square is equal to 2r whole square. It is nothing but 4r square. But the p square value here we have 2q square. That means 2q square value is 4r square. So q square is nothing but 4r square by 2. It is nothing but 2r square. 2r square is in the form of multiples of 2. Multiples of 2 always divisible by 2. Therefore, q square is divisible by 2. So q square is divisible by 2 means q becomes divisible by 2. Hence q is divisible by 2. Now observe that P as well as Q. Here both P and Q are divisible by 2. Both P and Q are divisible by 2. Now coming to the definition of the irrational number. What is the definition of the irrational number? P by Q and Q not equals to 0. Both are integers and HCF of both P and Q is 1. But here both P and Q is divisible by 2 means the HCF of P and Q we are getting 2 instead of 1. So that is a contradiction. Whenever P by Q is a rational number, the HCF must be 1. But here HCF we got it as 2. Therefore, it is wrong as per the definition. Why we got wrong? We assumed root 2 as a rational number. We assumed root 2 as a rational number. That is wrong. That is the contradiction. Therefore, our assumption is wrong. Therefore, root 2 is irrational. So this is the method, indirect method to prove any irrational number as a irrational number. So in the case of using the indirect method of proof, we will assume whatever to be required as a false statement, and we will move on with the procedure. Somewhere we will get the wrong statement. So by that means we will get what thing is taken wrong as a correct thing. That is a method of indirect proof. Now, not only root 2, we can prove root 3 irrational numbers, root 5 and root 7, so on.